So today's lesson is on ionic bonds, and this is the simplest one to get started on bonding and Lewis dot structures. That's why we're starting on it, because it's a very simple bonding type, and it doesn't happen all the time, but it's very frequent. It does appear quite frequently. The basis of it is that electrons give away, atoms with spare electrons will pass them on to atoms that need extra electrons in order to become stable. So in this case, this yellow electron here gets passed in here to make this one stable, and this one also becomes stable as a byproduct. So it's a win-win situation for both of them. So we'll look at why and how things are supposed to be stable in this lesson, but this is just a primer on it. So obviously the first thing to look at in ionic bonding is stability, and what is it? So in order for an element to become stable, it has to achieve an electron configuration similar to the noble gases. The noble gases are already stable. For other elements, they all aspire to be like those noble elements, those noble gases. In order to do that, they need to have an electron configuration that sort of approximates a noble gas configuration as best they can. The closer they are to a noble gas structure, the more likely they are to be stable. And in order to do this, the best way to understand it is there has to be 8 electrons in the outermost shell. So if we had a substance that looked like this, so that's our nucleus, there's our one shell, 2 shells. There was, 400,000 shells. I would just draw 400,000 shells in. But the key is that the outer one has to have 8 electrons. Okay, so this one here has to have 8 electrons in it. If that outer shell happened to only be the first shell, so if this atom only has 1 shell, then you only need 2. Okay, so 8 if you have more than 1 shell, 2 if you have just 1. That's what we're looking for. And you can see here, this guy is pretty happy. He's got 8 electrons in his outer shell, and he's this nice yellow. If I was to draw a happy face on him, that's what he'd be. That's the key, 8 electrons. So just remember that. That's a big part of chemistry sorted right there. So in order for this to happen, electrons have to be shared or donated by another atom for stability to be achieved. Obviously, if I don't have 8 electrons straight from when I'm born as an atom, so me as a chlorine atom, if I don't have 8 electrons now, I'm not ever going to just grow an extra electron. That doesn't happen. It doesn't just pop up randomly. Someone has to give me that electron in order for me to achieve stability. And that's the key here. I need to get that electron from somewhere. And the question then becomes, where do I get that electron from? So before I talk about why things, why do certain things give away electrons and why certain things don't, I'm going to talk about Lewis dot structures or diagram, because in this lesson we're going to see a lot of these Lewis diagrams. If you don't understand them, obviously you're not going to learn anything. So we need to talk about this first before we can talk about any of the other stuff. So Lewis dot diagrams are basically used to allow chemists to track the movement of electrons in a chemical reaction. I'll get to what this actually means here in a sec, but maybe you've figured it out already. So that's the whole point of them, just to allow us to track electrons as they move between certain places. So in order to draw these Lewis dot diagrams, you simply take the chemical symbol of the chemical in question. In this case, we're going to take chlorine. We just write the chemical symbol and draw dots around it. Okay, that's all. Just draw dots. Okay, so that's all it means. So if I was doing oxygen, I've got O, and then I just draw dots around it, okay? Etc. And the reason I kind of hesitated with O just then was because drawing circles around a circle kind of doesn't really make sense. Now, the number of dots that you draw around, so these guys, is equal to the number of electrons in the valence shell. That's why I'm getting to this now. So if you look on your periodic table, which I'm hoping that you have with you, you see that chlorine is in group 7. And that means that it has 7 electrons in its valence shell. And that means, if you count these, there are 7. So the Lewis dot diagram is correct. So that's what we do when we draw a Lewis dot diagram. Just the outer shell. We don't need any knowledge about what's inside. For instance, sodium, then potassium, and lithium. Their Lewis dot diagrams all look exactly the same, except for the symbol, because they all only have 1 electron in their outer shell. So bar the symbol, the dot diagram is exactly the same. And that applies for all groups. They all should have the same diagram, except the symbol in the middle changes. So now that we know what Lewis dot diagrams are, we can move on to understand ionic bonding. So ionic formation. So some elements can achieve stability by taking electrons into its valence shell or by removing them from their valence shell. When this happens, there is an imbalance in the number of electrons compared to protons, and this means the new particle has a net charge. So what do I mean by that? Well, if you look at, these new particles are called ions, okay? So when an atom gives away an electron, or an atom takes in an electron, there's an imbalance in the number of protons and electrons, so you get a charge. So for instance, let's look at sodium here. It's got 1 electron in its outer shell. Now, in order to get 8 in its outermost shell, it needs 7. It needs to collect 7 electrons. Now, alternatively, it could cheat and say, look, you know what? I don't really care about this electron. Why don't I just get rid of it? And then I'll have a full outer shell because I don't have that shell anymore. So if I lose this electron, I lose this entire shell, which means that now all of a sudden I have a full outer shell. So it kind of cheated. Now, if that was to happen, if you count, there's 11 electrons to start with. Then afterwards, it becomes 10. Now, its number of protons is 11, and after, it's still 11. So you can see that here, it was balanced, whereas here, now there's 1 more proton, which means that the sodium will become the sodium plus ion. So that's why. And so we've got a positive ion. Now, if you look at the chlorine, on the other hand, now it can't pull the same trick as sodium. It can't say, look, I'm going to drop this outer shell, because it's got 7 in its outer shell. So that means that it can just collect 1. And it happens that sodium wants to give away 1. They're both happy. So you can see that it grabbed that electron, this X here, and all of a sudden, it's now got a full outer shell. Now, before, it had 8 plus 2 is 10, and it had 17 electrons to start with, and 17 protons. Now it has 18 electrons and 17 protons. So you can see that there's 1 more electron than there was proton. It will become negatively charged. So that's how ionic bonding works. So we'll look at it more closely now. So the chlorine atom and chlorine ion. So let's look at the chlorine atom. It has 17 electrons in total and 7 in its outer shell. Okay, so if you count all those dots, you'll definitely see that. In order to achieve stability, it only needs 1 electron more. It only needs to fill this 1 space here. If it does get an electron, there will be 18 electrons, but only 17 protons. And you can see that it's filled with an X here, because that's just an electron from another atom. So in Lewis diagrams, you tend to represent electrons from one atom with a certain symbol, in this case circles, and another atom will have electrons represented by something else, say X's. Okay? I just like to use that because it helps me to sort of track which electrons are going where. It's just a little trick that I use to neaten up my diagrams. Now this means that the chloride ion will have a net charge of -1. Now the sodium atom and sodium ion, now if we look at the sodium atom, it has 11 electrons in total and 1 electron in its outer shell. So here we have, you can count that out for yourself. It could try to collect 7 electrons, but the key thing is that it could give away its 1 electron and lose that shell. So here it has 3 shells, but here it gave away that electron and has now 2 shells. Since it's easier to lose 1 electron than gain 7, losing electron is more likely. The sodium ion now only has 10 electrons and 11 protons, so the sodium ion has a net charge of +1. Okay? So that's why we get positive and negative charges. So now we're going to look at an ionic bond. When an element that gives away electrons comes into contact with one that absorbs electrons, you get 2 ions, right? One positive and one negative. So if we look at our animation here, we've got one that gives away an electron and one that takes an electron. This one becomes positive, this one becomes negative. Okay? So here's our animation for you. So when the electrons have been transferred, the 2 ions are attracted to one another by electrostatic attraction. Okay? So when these 2 form ions, this one's positive, this one's negative, they attract each other, just like opposite poles in a magnet. You've got the north pole and the south pole, and they attract each other. Similarly, these 2 attract one another as well. And that forms an ionic substance. So this attraction is what we call an ionic bond. So when these 2 come together, the bond that they form is called an ionic bond. And the substance made up of ionic bonds is an ionic substance.